Hello everybody, my name is Kylie and I'm a student at MIT studying physics. That's what my major is. And today I'm going to be showing you some astrophysics presets from a variety of astrophysics classes that I've taken. So the first one we're going to be looking at is 8224, which is MIT's black hole class. So if we take a look, let's take a look at a random one, perhaps how about problem set 3. So as we can see here, we have a problem on killer tides. So it says, it is sometimes said that an astronaut falling into a black hole would feel nothing peculiar as he or she crossed over the event horizon. Discuss whether this is true and how the statement depends upon the black hole mass using the following approach. Then it lists what you have to do. So a problem on the tidal forces, pretty cool. The second problem is radial motion of a photon. So starting from the Schwarzschild metric, show that photons moving radially travel at the coordinate speed of light, and it gives it to you. So a lot of problems at MIT in the physics department involve trying to prove that a certain relationship or equation that you know is true. So that's why you kind of see these things like that, and like this. Okay, the third problem is the photon's circular orbit. Starting from the Schwarzschild metric, find an expression for the coordinate speed of light in the phi direction. So lots of different questions about the photon circular orbit. So all of these questions, they really rely on you having previous knowledge and general understanding of the topic, and then have you prove some small portion of it. So last couple ones. Number 4, communicating with life on Venus. Because of the recent discovery of phosphine on Venus. Yeah, this class took place during the semester where there was a discovery about phosphine on Venus. Astronomers decide to try and make contact by sending a radar signal from Earth towards Venus when Venus is on the far side of the sun. The signal reflects off Venus and travels back to Earth where the total round trip time is recorded. Ignoring the effects of gravitational bending, just use the results of problem 2 to get a numerical estimate of the effect of the sun's gravity on the total round trip travel time. So another common thing that PSETs will have is they'll say like, oh, use the results of a previous problem, or like the concepts kind of stack as you go through the problem set. I think that's pretty cool because you learn more as you go through the problems. But it can also be kind of bad because what if you really screw up one of the earlier problems? So you have to really make sure that you're doing okay the whole entire time. Okay, and the last problem, black hole spin. Compare the maximum angular momentum of a 1.4 solar mass black hole with the angular momentum of the fastest known pulsar, which rotates with a period of 0.00139 seconds. So yeah, they don't give you any equations or anything. You have to either, recall back to previous lectures or lecture notes, or logic your way through the problem. Yes. Next, we're going to be taking a look at 12425, or 8290, which is MIT's exoplanet class. I pulled up a random PSET here, PSET 6, and we're going to take a look at that. First problem is on black body radiation. So it gives you the equation for the black body radiation and then defines the different variables for you. And then it asks you some questions on that. So derive Wien's law. And then it asks which wavelength is Earth's thermal emission brightest. Then it asks for the same for hot Jupiter, which is a type of exoplanet. And then it says to derive the Stefan-Boltzmann constant. And in which wavelength is Earth's reflected light brightest? So lots of questions about black body radiation. Second problem says use the Archer computer code interface that we used in class. So yes, in this class we took some time to look at a lot of different websites and cool little thingamajigs online to kind of visualize the stuff we were learning. So it asks, identify the major gases in Earth's IR thermal emission spectra. It's infrared. It says, how do clouds affect the appearance of Earth's infrared spectrum? And it says, choose a greenhouse gas and increase the gas by a large amount. What is the surface temperature increase required to preserve the same total outgoing flux? And the third one, Earth's atmosphere emission looking down. Plot Earth's atmosphere emission looking down from different altitudes. Start at 0 kilometers and then increase by 2 kilometers up to 10 kilometers, and so on. So this is a question about atmospheres. So in this class, we really addressed all different kinds of aspects of planetary science, including atmospheres and emission and radiation and things like that. So that's what this problem set was all about. Okay, for the last PSET, we're going to be taking a look at 8286, which is MIT's Intro Cosmology course. It's called The Early Universe, and it's taught by Alan Guth, the creator of inflation. Pretty cool. So as we can see here, the first problem is about a circle in non-Euclidean geometry. So a large portion of this class is learning to deal with non-Euclidean geometries, which is basically when you're not working in flat space, so curved space. So there's a problem on that involving a metric. Second problem is a volume of a closed universe. So cosmology deals with learning about different kinds of universes, and this problem involves a closed universe in particular. So it gives you the metric of a closed universe, and then it gives you some hints about how to get this volume. So it says to break up the volume into spherical shells, and then use this, which is the metric for the surface of a sphere. Problem 3, surface brightness in a closed universe. So more closed universe problems. So we have the space-time metric again for homogeneous isotropic closed universe. And then, let's see. It says that the metric simplifies to this form, and then it gives some problems on that. So it says the form of A of t depends on the nature of the matter in the universe, but for this problem you should consider A of t to be an arbitrary function. So we did that a lot. So there are a lot of really complicated aspects of cosmological equations, but we always just, simplified them so that we could learn the concepts in this class, because it's an intro class. There's a grad level cosmology course at MIT. I'm sure they would go more in depth into that. So more parts to this problem. Surface brightness. All right, problem 4, trajectories and distances in an open universe. So instead of a closed universe, we now are working with an open universe. So we work with all kinds of universes in this class. So this is basically a similar problem to the other ones. So we're given the metric for homogeneous isotropic open universe this time. And then it also simplifies to another form, just like the previous problem. And then it asks some questions about the open universe this time. So similar diagrams to the previous problem. Lots of different parts. All right, problem 5, the Klein description of the GBL geometry. So it references the lecture notes. So oftentimes classes will do this. It'll be like, oh, I explained this so-and-so equation or concept in the lecture notes. Try and apply what I did there. So we have this that was referenced in lecture notes 5, it says. And it says the problem is to prove the equivalence between those two equations. So luckily for us, we don't have to do that just based off of coming up with random ideas. Instead, we're walked through it with different parts. And so this is very common in a lot of PSETs in the physics department at MIT. They'll break down the problem for you to show you exactly how you're supposed to do it, but not give you the answers. So they'll give you some steps for you to take so that, you aren't floundering around trying to figure it out, but you still do have to do the work yourself. They'll just give you some hints by breaking it down like this. Sometimes if you can't figure out how the parts kind of go together, it's kind of difficult, but I guess that's what going to office hours is for. So we see here, they work us through it. And then we have problem 5 from problem set 4. So this problem was introduced a week earlier so that students would have longer time to work on this problem. So it's basically making a proof. So this problem was extra credit because doing formal mathematical proofs is not a requirement for any physics class. That would only be for math majors. So basically, if you knew how to do formal mathematical proofs, you could work through this problem and submit a proof. Or if you didn't know, you could learn and then try and do this problem as well. Yep. So those were 3 astrophysics PSETs from previous classes that I've taken at MIT. I hope that y'all learned something from it, and I'll see you again next time. Bye-bye.